Let's solve this homogeneous linear equation with the constant coefficients. In this question, we have been provided the initial value conditions. This means that we will eventually be finding the values of C1, C2, and C3, which are the arbitrary constants we always leave behind in the general solutions. This will be giving us our particular solution. Since it is a homogeneous equation with the constant coefficients, we know that the first solution is going to be e power mx. Then we are going to be finding the y prime, double prime, and triple prime, and substitute these values into the homogeneous equation. Substituting these values in the homogeneous equation, then we will factor out e power mx, which will be common in all three terms. We know that e power mx cannot be equal to 0, so we will directly be writing the auxiliary equation here. Let's carry out trial and error method to find out the first factor of this cubic equation. Let's assume that m minus 1 is the factor of this cubic equation. So we'll be using m is equal to 1 and substituting this value here to see if it satisfies the given equation. So 1 cubed minus 3 plus 4 is not equal to 0. This doesn't satisfy the cubic equation. So let's assume that m plus 1 is a factor of this cubic equation. Hence, we'll be substituting m is equal to -1 and seeing if it satisfies the given equation. -1 cubed minus 3 times -1 squared plus 4 equals 0. So this gives -1, -3 plus 4 is equal to 0. Hence, the equation is satisfied. This means that m plus 1 is one of the factors of this cubic equation. So let's find the other two factors of this cubic equation. Let's carry out a synthetic division, writing the coefficients of this auxiliary equation. Writing 1 as it is, multiplying 1 times -1, and writing it here. Now repeating the same process. This remainder is equal to 0, and these are the coefficients of the quadratic equation. So let's rewrite this auxiliary equation. So the roots of this equation are -1, 2, and 2. You can see that all of these are real numbers. However, these two are repeated twice. So we'll be making this general equation. So we'll be making this equation for the general solution. And this too is going to be substituted here and here. So this is the general solution of the differential equation given above. Now, in this same question, we have been provided the initial conditions, y of 0 equals 1, y prime of 0 equals -8, and y double prime of 0 equals to -4. So first, let's manipulate the equation and find its first derivative and its second derivative. This is the same general solution of the equation we are doing right now. The e power 2x is common in both of these terms, so we'll factor out e power 2x here. Now let's find the first and the second derivatives. So far, we've only found the first derivative. Now let's move on and find the second derivative of the function. Now you can see that we can add these two terms. So this will be making 4c3 e power 2x. Once we have found the second derivative, we can now apply the initial conditions that have been provided to us. These are the initial conditions. And here, this 0 is for the x. So in all three of these equations, I'll be substituting x is equal to 0. After we have got these three equations, we're going to solve these equations using Cramer's rule. We're going to be taking the coefficients of C1, C2, and C3 and write down the coefficient matrix. So we're going to write it like this. You can see that these are the coefficients of their corresponding equations here. So for example, for this row, the coefficient of C1 is -1, which we wrote here. The coefficient of C2 is 2, which we have written here. And the coefficient of C3 is 1, which we have written here. Now, we're going to be writing these C1, C2, and C3 like this. And then we are going to write the constant column, the right-hand side of the equations, which is going to be denoted like this. Now, let's find the main determinant, which we call delta, represented like this. This is the determinant of the coefficient matrix, this one. Now, let's find the determinant using the cofactor expansion. So the determinant is equal to This is how we are going to use the cofactor expansion. We're going to take the first row and expand along it. Here's how to do it step by step. First element, this one, found at the first row, first column. Take this element and ignore the first row and first column, and take the determinant of the remaining 2 by 2 matrix, this one. So here we wrote positive 1 multiplied by the remaining 2 by 2 matrix. Now, for the second element found in the first row and second column, we'll be taking this element, but with a negative sign, because when we will be moving along the row, the signs will go like this: positive, negative, positive, negative, and so on. So taking the negative one here, we wrote it here, and ignoring the first row and the second column, we took the determinant of the remaining 2 by 2 matrix, which is this one. Eventually, reaching the third element, which is 0, we'll be taking this, ignoring the first row, third column, we'll be taking the determinant of the 2 by 2 matrix. But since it is being multiplied with 0, the entire determinant here can be ignored because it will become 0. Now let's write it in proper format. This is how we took the determinant. We did 1 multiplied by, when taking the determinant of 2 by 2 matrix, we first multiplied 2 with 4, and then, placing the negative sign, we multiplied 4 with 1. This is how we find the determinants. In same way, we have found the determinant of this, and this was completely ignored because it is 0. So let's rewrite this, and we find the base determinant as equal to 9. Now that we have found the base determinant, delta, we can proceed to find the values of the variables C1, C2, and C3 using the Cramer's rule. To find the value of C1, we'll be using the formula delta 1 divided by delta. We know the value of the base determinant, and to calculate delta 1, we are going to be replacing the first column of the original coefficient matrix with the constant column. So, first column of this is going to be replaced with this, like this. Hence, we are going to get this result. Now, at the same time, we'll be keeping the second column and the third column the same. Here, you can see that the second and the third columns are written as it is here. Similarly, to find the delta 2, for finding the constant value C2, we replace the second column of the coefficient matrix with the constant column, like this. And to find the value of delta 3, we replace the third column of the coefficient matrix with a constant column here. The respective results are written here. Now that we have found the values of determinant, delta 1, delta 2, and delta 3, and we know that the value of the base determinant is equal to 9, we can find out the value of C1, C2, and C3, which is equal to delta 1 divided by delta, and for this, delta 2 divided by delta, and for C3, delta 3 divided by delta. Now, substituting the values in their respective positions, this 32 here and this 9 here, we'll be getting 32 divided by 9. For this, we'll get minus 23 divided by 9. And for C3, we are going to get 6 by 9, which is equal to 2 by 3. Now that we have found the values of C1, C2, and C3, we'll be substituting them back to the original equation. This was the general solution at first, but when we are going to be substituting the values of C1, C2, and C3, it is going to be giving us our final answer, which we'll be referring to as particular solution.